So there's a couple different layers to this. I'm going to break it down into a couple pieces. So there's a few different lenses to look at how data exists on the network. If you've seen some of the previous streams, I've talked about it before, but holistically, I don't think we've actually covered it in recent history, so it's worth the review. So the nature of the network in terms of how it actually generates proofs is basically a constructed Bloom filter. It's not quite your traditional Bloom filter where you're trying to detect data availability or the lack thereof. It's basically a container method that structures our settlement of data in a relatively randomized way, but still deterministic, such that we have, boy, this is going to be a pain to copy, so I'm just going to, whoa, this is going to be a pain to copy, so I'm just going to bring that over like this. Obviously, this isn't precise, but essentially there's 256 individual global shards. And basically, every single one of those individually contains a lot of data, but the nature of how data is forcibly replicated through the network requires that 3 different shards actually contain the same data for that given material. So while, if you use a Bloom filter and you're familiar with this concept, basically you take several hashes of data and then use modulo arithmetic to dictate which points of bits on that string of data it corresponds to. We're basically doing the same thing based on the address, like the application address of that data. It ends up picking which 3 of the global shards it corresponds to. So from that, we then have the actual individual app level hypergraphs. And so from there, let's just pick 3 random ones for the sake of example. Each one of those will then have contained the root of that particular hypergraph. So hypergraphs, if you're not familiar, are essentially the same thing as a regular graph, except an edge can connect multiple vertices together instead of just 2. So basically, when you have a hypergraph, you can relate over data in ways that have higher dimensionality than a graph. The other unique thing is that depending on the structure of a hypergraph, a hyper edge, as it's called, can actually contain not only vertices but other hyper edges. And that extra layer of dimensionality basically presents a very convenient and efficient way to represent higher dimensional relationships, which are really important if you're wanting to encode things like a relational database into the form of Q's hypergraph. So from there, we have the app level hypergraph layer, and what that amounts to is 4 individual sets. So for those who are familiar with CRDTs, what that is, oh Lord, what have you done, Excalidraw? Oh God, why? Okay, decided to screw up the arrows the moment I decided to resize that box. I'll just leave it out for now. So anyway, the structure of the hypergraph data set is essentially a two-phase, 2-set CRDT. And what that means is that you have essentially a set for vertices being added, a set for vertices being removed, a set for hyperedges being added, and a set for hyperedges being removed. This is important because the way that data gets added to the network is distributed across many different nodes and replicated only by a small handful of nodes that relate to that specific shard. And so when you need to, for example, prove, let's say that, for example, right now, as the network's encoding this data onto the encrypted hypergraph, not every node is going to contain every token. And so you want to be able to prove to the network that that token is actually there and exists and hasn't been spent before. Otherwise, you could run into problems with double spending attacks. And so a couple networks have different ideas around how they try to do this with their shard model. Vlad Zamfir had that neighbor shard model that got used very rarely. I'm trying to remember which one it was. Oh, God, I can't remember the name of it, but there was one network that tried to use that approach, but it has intrinsic scalability limits and also is a giant pain in the ass to deal with. Ethereum abandoned their entire sharding roadmap, so who knows what they would have actually settled on if they had settled on anything. And then you have certain protocols like Near, which their Nightshade consensus protocol is not real shards in the sense that those shards are individually handling data that's uniquely mapped to it, but instead it's more of like a trust of these individual sets that can independently scale out throughput rather than actual data settlement. So there's still at the global level, still all of those transactions have to be validated by the same set. And so it's really a throughput thing rather than an actual scalability thing. Okay, yeah, a question real quick. Where is the S3 data actually stored? If it's distributed, can the node runner control which node on the network this data is distributed to? So I'm not sure what you mean by that. Like, if the node runner can control which node their own data that they're putting through queue storage is distributed to, the answer is no. Nodes are permissionless. So if somebody wants to replicate a shard that has specific data and they know it has specific data for some reason, you can't control which node is actively covering a shard. But nodes can individually control what shards they're covering. So there is that. And that's actually kind of a useful topic to bring up real quick, because obviously, like, having a very large data host, we've already seen this happen in protocols like IPFS. Sometimes there are bad people who do bad things and they will try to host their data on it because it's less likely that they'll get deplatformed on IPFS than, you know, if they were using Amazon S3 or something. We've seen this happen a lot. And the difference is with IPFS, like, you have to do this approach where you're basically unpinning data so that you don't host it. And there's like this abuse process, which doesn't work very well, but it exists. With Q, it's different. We do have like a way that can uniquely prove like the data that exists here. Even though it's encrypted, we can prove what it is if we know what it is. And so by consequence, a node operator, if they wish to choose to not share data, even if that data was redistributed against like different app shards or something, they could explicitly like block it out and say, no, I'm not replicating this. So there's a little bit of control at that level, but the control is at the node operator level for what data that node is willing to replicate versus somebody controlling which nodes are replicating their data. That's the inversion there. Okay, so we have this basic structure. So at the app level shard, so let's talk about this from in terms of tiers of layers. So there's layer 1, which is the global level. This essentially amounts to 19 kilobytes of data, essentially encoded points for BLS 48581. So that's structurally where that data resides. And then at the app level, that's essentially level 2. And then finally at the underlying vertex tree level and hyperedge tree level, that's where we start to get into the third layer, which is a little bit more complex than L1 or L2. And so what I was saying here is that at the layer 2 level, these 4 individual sets constitute the collection of data that's being replicated through the network. So on a given app shard, so for example, the token app as we're currently converting, there's actually not even the use of hyperedges in this case, because this data is actually relatively non-relational. There's a notion of like a you know, an owner of that data, but we don't actually provide a relational basis onto that through the hyperedges, because that could actually potentially convey information. And if the idea of the token is that it's privacy preserving, this would be one case where that information would actually leak some metadata that we don't want to leak. And so it's strictly encoded as vertices. And the way that that basically works out is 2 components. So to start things off, we'll talk about how that data is actually stored and addressed. So you've already seen the way that addresses are encoded on the network. It's those Poseidon hashes that are based around the actual data itself. I'm going to make this a little bit simpler because drawing out 64 nodes would be insane, especially when we have to do multiple layers of it. So I'm just going to do 8 here, but structurally, what we have is essentially a prefix tree. And so a prefix tree is basically taking the actual like string of data that represents that given address. So the address of a coin, like a coin object, not an individual unit of the token, but a coin object, lives at a given address based on the deterministic information that derives the address itself. And so the way that that works out in a prefix tree is that as data gets inserted into the tree expands outward based on the addressing scheme itself. So like, let's talk about this in terms of bytes. So we have like some random byte value, it's hex, so there should be like that. So basically runs out for 32 bytes. And based on how the structure of the tree itself works, there's 64 entries. So how do you pack that byte string into 64 individual buckets each way down the tree? So you have to think about this in terms of the actual underlying bits. So for example, the first byte is 98. So 98 would be, I have to think about that for a second. That would be 1, 0, 0, 1, and then 8 would be 1, 0, 0, 0. And then the next byte would be 0, 0, 1, 1, 1, 0, 0, 1, and so on. I'm not going to dive through all that because there's no point. So basically we have these individual 8 bits that make up each byte of the address, but this is 64 different units that it can fall into. So the way that a prefix tree works that's of degree 64 is we take it and we split it into log 2 of 64, which is 6, which means there's actually 6 bits that dictates which slot in the tree it falls under. So basically taking this long bit string, you chop it up into 6 bits, and then you actually derive which bucket it falls into. And so based on that information, you end up getting the actual path that it traverses through the prefix tree. So in this case, this would be, God, I have to do this arithmetic in my head. I'm not suited for this with such little sleep and so much caffeine. That'd be 32 plus 4, 36 plus 2 is 38. Okay, so that would fall under bucket 38. And then the next one would fall under bucket 3. And this one, I didn't finish filling out the bits on that, but it would fall into whatever bucket that it falls under. So that basically gives you the segment of paths. So starting from here, which would be whatever the root value is, which is usually going to be a prefix that is empty, like just no data. Oh, great. Okay, I'm not going to resize this because all the arrows screw up every time I do this, but basically empty array goes there. The next place it goes to is the 38th, really 39th because it's 0 indexed, but the 38th box on the tree. And then from there, it goes to the 3rd from there. And that's only if there's no shared prefixes that are coming into play that can compact it. So part of that means that, like, for example, like let's say we had, I'm just going to write these encoded in paths so I don't have to do conversion on the fly, especially when I'm this tired. So let's say that we have a decoded path that is like this. It doesn't really matter. It's just for the sake of example. So let's say we have that, and then let's say that the only other item that's also in the tree just for some reason conveniently shares the same prefix up to the 3rd point, and then it has other values from there. That means that when this gets encoded into the tree, these are the only 2 values that exist. These first 3 path elements actually end up encoded into that branch, and then it moves from there to box 0, box 1, and carries on for the rest of it. So that means that it's actually very compact. Like, you don't have to actually traverse out to the full length of the path that represents that particular address. And also one other thing to note that's pretty important is, as I said at the beginning, this is actually, like, positionally, you're dealing with a singular app address, but there's other app addresses that could get bucketed into those same global points. And so that address is not just the address of the object under the app, it's actually the app address plus the address of the data under the app. So it's actually a much longer string, it's 64 bytes in total. And so you'll end up with a lot that shares that same prefix for the given app. But what's cool about this is that unlike a Merkle tree, which, people who have been in crypto for a long time typically have a better understanding of what a Merkle tree is, generating proofs of that, for example, for a true Merkle tree, which is just a binary tree, means that you have to then get proofs for neighboring elements working all the way up the tree, and that gets computationally expensive. And it's even worse if you have to get proofs for a Merkle-Patricia tree like Ethereum uses. So what's really nice about the Verkle trees that we use is that they're very compact. Instead of having to generate those neighbor proofs, you can actually just generate the string directly. And so based on the amount of data that exists for any given application, it's essentially log 64 of whatever the total data set size is, and that's how many elements you'll need for your proof. And so that's actually very, very nice, compact, and efficient. And so what that means, and the reason why I was walking through all this, is that when the network is sharded out, you don't just have shards at the L1 level, you have shards at the L2 level, you have shards at the L3 level. So nodes, when they're doing this enrollment process, are actually saying, like, I'm wanting to hold only this prefix of the tree because that's just too much data if I go any higher than that. And the reason why this works is because this data is cryptographically verifiable. So the data itself, as it's encoded into the tree, like I said, we're using verifiable encryption, and I'll get to that in a second, but the actual positioning of the data on the network is also verifiable using cryptography as well because of these Verkle proofs. And so the shard basis that it cares about could be potentially like a third degree into the tree. Might not be starting out, but it could be. And so what that enables is the ability to prove in terms of the overall global state is at the global level from this 19 kilobytes of data that every node has. You don't have to provide any of the data about that. You can construct a point proof that shows for the given L1 to L2 down all the way through the vertexes or hyperedges, you have a very small compact proof that is approximately 5 to 6 points of data, which works out to 74 times 5 or times 6, depending on the size here, bytes of data, and that's sufficient to encode proof of existence of any data on the network. And the fun thing is that because this is a CRDT, there's corresponding adds and removes. So if data's been removed from the hypergraph, you can actually prove that it's been removed because the corresponding remove set has an entry for that. And so what you get from this result is a very easy, compact, efficient way to prove any data between shards without having to have all the shards in the network holding that data or doing some sort of receipt passing model where things get really complex and require a lot of state management. This is essentially stateless. And so that's the point of how the hypergraph exists and how the data is put into the network. But the other thing that I was talking about is verifiable encryption. And so Verkle trees are something that other protocols are also trying to implement or already have implemented. And so that's not particularly net novel. What is particularly interesting is how we prove that that data is what it is, despite the fact that you can't actually see the underlying data. And that's the cool thing about verifiable encryption. And to my knowledge, there is not another protocol that uses verifiable encryption at this time. I believe there are protocols that do like proof of custody of key material required to encrypt data, like in the, I believe, what is it called? They use terms like privacy enhancing technologies and kind of mask over the underlying implementations because it gets technically dense. But at the end of the day, they have some sort of custodial system that uses trusted execution environments to prove that the code that they're executing was, from an official release and was built deterministically and all of that, but ultimately it does have layers of trust. And so what we want to do, and one of the core values of Quilibrium, is that there is no trusted element. That's a non-starter for us. We do not it's for defense in depth, having TEEs is great, but in terms of actually providing security to the network, TEEs should never be the foundation of security. And so the way that we approach it instead is that we use verifiable encryption. And so what that essentially amounts to in the case of how data gets stored on the hypergraph is that we encrypt data using a process that is essentially called MPC in the head. And so if you're familiar with basic MPC protocols, you have essentially a couple of different computers, could be any number of nodes. There's specialized things for like two-party compute and so on. But in the MPC in the head approach, you could potentially be simulating up to 128 or even more than that to generate whatever statistical security parameter you've configured. And so the way that we're doing verifiable encryption is through this process that's used basically called robust DKG. And so when you do distributed key generation, most of the common models essentially construct a key based on some sort of polynomial. And so like if you're familiar with polynomials, the construction of them is basically like a of x, or a times x to the third plus b times x to the second plus c times x plus some constant d. Whatever the degree is, it relates to the number of parties, or at least the threshold number of parties in that given equation. And so what robust DKG essentially is a way that you're providing some zero knowledge proof commitments that information was generated correctly, and you can essentially have a higher bar of security that you're meeting by constructing this particular DKG process. Now, that's the MPC portion. In the MPC in the head portion, all of this is being simulated. And so what that means is that an individual node is essentially pretending to be each one of those individual MPC actors. And so instead of each party generating its own polynomial, one party is actually generating all of the polynomials for each simulated party. And the reason for doing this is that as you perform these interactions, you're also basically taking an execution trace of what you're doing that gives a way that you can essentially prove to any other node on the network that what you're doing is correct and you haven't done any sort of weird cheat. And usually the way this works is you have some degree of information that you're giving that is constructed based solely on how you're doing it, so that you're not actually revealing any private data, but you're instead just giving a reasonable bar. Like it's kind of like I guess one way to put it is like, let's say that you can always prove that I have like a red ball and a blue ball in my hand, and I like will put them behind my back, and you somehow know which one it is. And so me switching things up behind my back, I'm basically going to test you on this by asking you to tell me which hand has the red ball, for example. And you will go through this interactive process multiple times until you are sufficiently satisfied, or I am sufficiently satisfied, that you somehow have a way of proving that you know which ball is in which hand. And so the kind of process here of doing MPC in the head is essentially constructing a zero knowledge proof. Like it's conveying no information about the underlying data, but is sufficiently convincing to every other node, but like sufficiently convincing very compactly that data is correctly encrypted. And so that's basically how it works. It constructs a key based on this robust DKG solution, performs Elgamal encryption of the underlying data. The reason we use Elgamal encryption is because it actually slots really nicely both into this verifiable encryption scheme, but also how we construct transactions on the network. And so that's the final piece. Not intentionally a segue, but it actually works out really well as one. So one of the things that we were originally doing as part of the design of Q was to basically have every single act of execution on the network is utilizing these MPC in the head proofs, because it works really well in cases like verifiable encryption. What we found is that MPC in the head proofs get really expensive for certain types of interactions, and there's actually more concrete ways that you can efficiently implement proofs. And so the last place where this particular specific primitives came into play, as I mentioned in the previous broadcast, is around how we validate transactions themselves, like the transactions of coins. And so this is the final piece, and it's I was burying the lead on this, I guess, a little bit, but the way that I demonstrated creating a coin on QConsole is a way you can do it, but that's also very laborious and prone to error if you don't implement it correctly. And so what we're going to be rolling out is actually a streamlined way to do it that is strictly driven through Intrinsics. And so that way you don't have to do any QCL around it, and you can actually have some more interesting security guarantees that are reflective at a more broad level than having to actually summate over the data itself. So what that basically means is this. When a token is encapsulated as verifiably encrypted content on the network, you have this tree of data. And the way that we're breaking down the token structure itself is based on a few small pieces of information that are really important. The first is essentially proof of origin. So when a coin gets minted because of a worker constructing their proofs sufficient to mint it, we have the frame number that it originated from. And so that gets encoded into the first block of data about that coin. And so we have the frame number. Oh God, Excalibur, please be more helpful here. Okay, cool. So now we have the frame number. And then the next piece is the underlying amount. And so that is a 32-byte value because we honestly don't need to encode any more for that than 32 bytes. And I'll get into why that's actually kind of helpful in just a sec. And then we also have a piece of data that relates to the address it belongs to. So this is essentially a encoded piece of data that says, here is the owner of the coin itself. This is encoded in a way that you can construct signatures that proves ownership. So if you're going to spend that coin, obviously it uniquely identifies that, you're able to spend that coin and no one else. And that's also 32 bytes. And then the last piece, well, actually there's a bit more to that in a second, I'll get to. And then the last piece is essentially the, it's called the intersection. And the point of that is to essentially provide proofs if you are needing to for compliance reasons. Like one of the things that, for example, say that you are, sending tokens to an exchange. Exchanges care a lot about compliance. And part of how they care about compliance and enforce compliance is, most of them have block scanners that scan the entire chain and have full history of transactions, and by consequence, they're able to trace the lineage. Problem is, that's really invasive for privacy. They shouldn't have to know what everybody's up to. And so instead we have essentially this privacy preserving bundle that enables you to do intersection requests. So say, I'm sending a token to an exchange and they care about certain entities in the world that, this coin could never have originated from, could never be touched by them. If those addresses touched them, then it's game over. We don't want that coin. So this intersection bundle essentially enables them to test that without actually revealing even the history of addresses that touched it. So they're essentially able to only query for the addresses they care about. They can't just query for all of them because the address space is, 2 to the 256. It's like too massive to actually calculate. So they have to be concise with the addresses they care about. And that gives them a simple yes or no, like yes, this address touched it, or no, it didn't. And that's it. That's basically all that gets baked into it. I do want to be more specific about address though, because there's a couple of different addressing schemes that exist. So this data is actually encoded as a 0 byte in the existing data case, which is an implicit account. And then the second through 33rd bytes in that bundle is the actual address encoded as that Poseidon hash. And then there's also a domain component that's encoded as well. It's technically the 4th object, and the intersection is the 5th. But for the case of the currently converted items, that's just straight zeros because there's no data to contain there. So we have these blocks of data, and there's properties that we want to be able to confirm about them. And so part of the verifiable encryption process itself that's really unique is that you end up with what are called statements. And statements are essentially ways that you can cryptographically prove information about the data that's contained in that particular bundle. And so the verifiable encryption process is actually encoding not only the data itself, but those statements so that you can actually prove things about them. And so this gets back into the intrinsics I was talking about with how tokens are spent on the network. So instead of just encoding this data as straight line like data, where you just have the frame number, it's 64 bits, so you encode that 64 bits, the amount's 32 bytes, you encode those just like bit after bit, we actually pack it in a way that's a bit more efficient for constructing the kind of proofs that we're talking about. So instead, the frame number gets encoded, of course, as the frame number alone, but it's actually packed into a 55 byte value, but technically ends up being 56 bytes in total. So there's essentially 55 bytes that construct what the frame number is, then there's 55 bytes that construct the amount. So there's a lot of extra zeros that exist there, which sounds like it's inefficient. So why would we do it that way? And the reason is because now you get actually a very compact way to utilize how that data is encoded for the statements to construct proofs about them, so that you don't necessarily have to go through the process of doing these MPC in the head proofs for actually sending the transactions. You can actually just infer some of those properties from the data as it's already encrypted. And so what we do with that is we essentially construct two pieces of proofs. So when you send a token on the network, you are actually taking these bits of information and constructing a linear proof. And that first linear proof is essentially, like I have a token, I'm going to split it into two. And so you're basically proving, just like you would on a double entry ledger, you're essentially proving that, like, let's say that this is, maybe 10 quil, for example. It's obviously encoded a bit different because there's a unit basis to care about, but for the sake of example, this makes it easy. So say that we have, we split it into two, so now you have 10 into 5 and 5. And so this basically is a balance checking equation that says that when you take this and you subtract the output amounts, you end up with a zero quantity. Now, for those who are more familiar with field arithmetic, you'll know that there is modular arithmetic that comes into play. So now you have to also worry about, well, what if somebody constructs a 55, well, actually closer to 56 byte value that causes it to wrap around, and then you end up with some sort of infinite mint glitch. And so on top of the linear equivalence proof, we also have a secondary range proof. And so that range proof essentially proves that not only is it not, we preserve this linear property so that the equation is, equates to zero, we're also proving that these individual amounts must be greater than zero and must be less than 2 to 256. And so what that means is that we actually have a really compact way to encode how this data is accurate. So when you're sending it around for transactions, you don't have to actually go through this very complicated process of doing MPC in the head and then outputting, potentially absurdly large proofs if you need to split out your coins a lot, or if you're needing to merge a lot of coins. Instead, you can actually do a very compact, what's called a bullet proof. And so you end up with these two individual proofs, and then you have a proof around the signature relating to the address, and that gives you sufficient information to convince to any node on the network that the overall state is correct. So that comes from having verifiable encryption. So like I was saying, just for handling, like if you cared about what content was being replicated, this also allows you to construct really conveniently small proofs that can let you send data around on the network for transactional purposes and ensure that there is no infinite mint glitch happening. The other cool property about that is that because these commitments are actually linearly homomorphic, and the way that we actually set this data out onto the network, you can actually do a balance proof of the entire application state. So for a given token, you can essentially assert that there has been no extra quantity of coins that were minted out of spec of the protocol. So this actually gives you a great way at a glance to get a total balance of the network and prove that it has been operating correctly without actually revealing who's done what. But that being said, we actually do prove who's done what because prover information is public. So, long walk for a very complicated drink of water, but the purpose of this all is to provide privacy at every single level while still giving sufficient information to convince verifiers on the network in their individual shards that this information is correct, but constructed in such a way that it can be reasonably assured that each shard is individually proving over their data securely so that you don't actually have to check all the transactions on the network. Last piece that I wanted to talk about this relates to questions about how do you actually confirm that the network has, say for example, there's this form of attack that exists in like Byzantine fault tolerance discussions called essentially equivocating. So for example, like in a traditional blockchain, you would have, whoever the elected leader is for that round. Let's say they constructed a block, and then they send that block to one of the parties, and then they sent a different block that's competing for the same slot to another party, so that they could potentially send two transactions. And if they can't get the network to agree, it creates this potential that separate forks are running for long enough that they could potentially construct a double spend. So what's different for this is that the way that frames are constructed is that they are based on essentially an MPC process that we're using that not only provides essentially an assurance that data that was supposed to be included in the block is included in the block, so to speak, but it's also done by every party in the shard. So that RPM protocol that I previously talked about is how we essentially ensure that. And that gives you essentially an output value, which is correct by construction. You cannot equivocate it, such that every participant in a given shard already is sufficiently convinced that this was constructed correctly. You can't falsely equivocate two different frames from one another. It's guaranteed that the data included in that frame, because every single member of that construction witnessed it and it's been committed to as part of the process of generating frames, you know for a fact that there has been no equivocation, and there can be no equivocation. So that's like the super cool property that basically lets you have all these shards independently being done. It gives you the balance proofs that ensures that the overall integrity of transactions are consistent and can't be double spent, or potentially like weird modulo arithmetic to like infinite mint, and that winds all the way up to the L1 proof. And so from that 19 kilobytes of data, you can actually prove the entire state of the network. That's the really cool punchline to all this. The second thing that I was going to bring up about that is that token proof, that token intrinsic. We're not just going to make that part of the core network primitive for the Quil token. This is actually part of the generic token intrinsics. So people who want to launch tokens on Quilibrium are going to be able to utilize this intrinsic all the same. So they're going to be able to enforce that same rule set, come up with different minting processes that are some sort of verifiable approach based on whatever their need is, or if they just have like a mint authority for like, NFT style things, or just like a static, like here's the amount that's been minted, so on and so forth. And so from that intrinsic, you can actually just generate a token, and then you want to attach any metadata to it, you can just use the hyperedges to loop in whatever metadata you want to sufficiently construct it. So if you wanted to do a collectible, for example, you can just do those one-of-ones, mint them out, and then loop that in through the hyperedge to the given metadata that you want to represent. And so instead of having to do like this complicated QCL deployment, as I was showing in the previous broadcast, you can actually just do it straight from the Q console, just Q console, or sorry, yeah, Q client, token generate, and then it will generate an address and you work from there. So that's the whole process. That's the deep dive. I know that might have been like deeply nerdy for some folks, but this is like very pertinent information because this is what structure belies the entire protocol security. So it's important to go over it and explain how that all works, and essentially what the beacon is doing right now is converting everything into this encoded format. And so it's going to take a few more days, but that's essentially how it works. That being said, we are now coming up on the hour, so we're going to have to wrap it up at this point. I will take the couple of minutes remaining to answer any questions if anybody has any additional questions to add. Also check a couple of other channels where those questions might be coming up real quick. All right. Don't see any there. Let's see if there's any here. Cool. All right, folks. Well, I guess that wraps everything up. I know that this is a super nerdy broadcast, and so thank you all for sticking around for it. If you're not a bunch of math nerds like I am, hope that at least the cool impacts that come from this math is exciting to you all, because this is what we're going to be writing into 2.1 with, and it's going to enable a lot of really amazing possibilities. So happy to have you all here. And like I said, we'll go ahead and cover the remaining items in the Sunday broadcast, and we'll dive into the deeper details of the remaining bits of QConsole and QClient during that time. And it should be pretty close to when we're wrapping up the conversion of 2.1's network state too. So that's going to be really exciting. So cool. Glad to have you all here, and I will catch you all in the next one this Sunday. All right. Bye, everybody.